Boys are a girl's best friend.
Hi, I'm Yassmin.
And I'm Olivia. And today we're going to be talking about the chemistry behind gemstones.
Every girl's best friend.
The most common source of color in gemstones is actually caused by what's considered to be an impurity, the presence of a small amount of a transition metal ion. Without any impurities present, all gemstones would be colorless. This color can be seen as a result of the transition metals quantum mechanical model, which we studied in Chapter 3. Each d orbital can hold a maximum of 10 electrons, so the electrons that are present can be arranged in a wide variety of organizations. Based on the arrangement of the electrons, the 3d orbital will have a different amount of energy. The energy levels appear to us as different colors. When the atom absorbs energy, the electrons become excited and move to higher energy orbitals. The excited electrons return to ground state by releasing energy in the form of light in a process called fluorescence. One example of this can be seen in rubies, which are a crystal of the mineral corundum, a form of aluminum oxide, Al2O3. Pure corundum appears colorless because neither of these ions absorbs any light. If, however, a small portion of the aluminum ions are replaced by chromium ions, ruby obtains its well-known red color. Chromium, in this case, is considered an impurity. However, because aluminum and chromium ions have the same charge and are approximately the same size, this change has relatively little effect on the structure of the crystal itself. Aluminum and chromium do differ, though, in the number and arrangement of their electrons. The electron configurations for each of these ions can be seen written up here. Aluminum has a 1s, 2s, and 2p orbitals, each of which is completely full. Chromium has 1s, 2s, 2p, 3s, 3p, and 3d. The 3d orbital, however, is not full. It only contains 3 electrons, while it can hold a maximum of 10. Each individual orbital holds 2 electrons, each with an opposite spin, based on the Pauli exclusion principle, as we can see here. Because chromium's 3d orbital is not entirely full, the electrons in that orbital can be arranged in many different ways. Each arrangement has a different energy level, which appears to us as different colors. In this case, the vibrant red of a ruby.
Another way that colors can be created in gems like this diamond is by way of intervalence transition or charge transfer. Intervalence transition occurs when there are 2 different elements that have 2 different oxidation numbers. In Chapter 10, we learned that oxidation numbers are real or hypothetical numbers that are used to describe redox reactions with covalent reactants or products. Intervalence charge transfer entails the transfer of an electron from one transition metal ion to another. This reaction, or this intervalence charge transfer, is fueled by the absorption of energy in the form of light energy, and this in turn gives off a color. Okay, so let's pretend that I'm one transition metal ion and Olivia's another transition metal ion. And we both have different oxidation numbers. So what's going to happen is I'm going to absorb some energy from the light that's coming off from that lamp, and the electrons are going to get excited. So it's going to hop to that metal ion. So the electron's all excited now, it has to return to where it started from, and to do that it has to give off energy in a process called fluorescence. So it's going to hop back. And this is just going to, it's a continuous motion, so it's going to hop back and forth, back and forth. Intervalence transfer only occurs when the outer orbitals of the metal ions are overlapped, so the electrons can be transferred from one to the other, and this occurs continuously, so they hop back and forth, back and forth. For the color to be created by impurities, 1% of the mineral has to be made up of that impurity. However, for color to be created by intervalence charge transfer, only 0.01% of that transition metal ion needs to be present.
The colors of gemstones can further be caused by yet another defect, known as color centers. Color centers are caused by exposure to radiation, which causes a vacancy within the crystal structure. Because of the exposure to radioactivity, the electrons can move around from their normal site, lose energy in the process, and eventually become trapped within the vacancy in the crystal structure. The electrons that are trapped within these crystal structures are only able then to absorb certain wavelengths of energy. Therefore, they only emit specific colors that we see. We learned all about energy levels in Chapter 3. One example of a gemstone whose color is caused by a color center is the green diamond. The green diamond is a regular diamond missing one carbon atom. The carbon atom normally absorbs only red photons. Therefore, when it's missing, the diamond appears green.
The crystal structures of gemstones differ. Each different structure has a different effect on the chemical and physical properties of gemstones. In Chapter 4, we learned that ionic crystals are an array of ions that are positioned at regular intervals in a crystal lattice. The crystal lattice itself is made up of individual unit cells that give the crystal its characteristic shape. Some gems, especially those containing quartz, are network solids that contain compounds and not elements. Diamonds, on the other hand, are carbon-based network solids. There are other gemstones, such as the precious opal, that are amorphous solids. Amorphous structures are solids that are composed of molecules that are not arranged in organized crystalline structures. This gives rise to many physical properties for the amorphous solids. The crystal system is a grouping of crystal structures based on the axial system used to describe their atomic lattice structure. There are 7 different such crystal systems. The cubic or the isometric system is characterized by total symmetry and includes crystals that have 6 faces. Gemstones with this crystal structure include diamonds and garnet. Hexagonal crystals have 8 faces and include the famous gemstones aquamarine and emerald. The gemstone zircon is in the tetragonal crystal system that has 6 faces and 3 axes that meet at 90 degrees. The rhombohedral or trigonal crystal system includes the rubies and sapphires. The crystals in this system have 6 faces. The orthorhombic crystals have 6 faces, and the gemstone topaz is amongst these crystals. The monoclinic crystals have 6 faces and 3 unequal axes. Azurite is included in this crystal system. Lastly, triclinic crystals have 6 faces, and one gemstone in this group is vibrant turquoise.
Let's see what happens when we place this sample of a diamond into the universal solvent, water. As we can see, nothing happens. Why is that, you may be wondering? Well, gemstones are insoluble. As we learned in Chapter 9, if a substance, such as a diamond, is insoluble, that means that less than 0.1 grams of that substance dissolves in 100 milliliters of solvent. If a substance is slightly soluble, that means between 0.1 grams and 1 gram will dissolve in the same amount of solvent. And finally, if a substance is considered soluble, that means greater than 1 gram of that solute will dissolve in 100 milliliters of solvent. This is an example of a crystal lattice structure, such as the ones that form gemstones. While this may not be the exact structure of a gemstone, as a visual aid, it'll serve the same purpose. If we refer to the solubility rules, we know that breaking apart a crystal lattice structure is an endothermic process. Therefore, in order to break apart this diamond structure and cause it to dissolve, we would need to add energy into the reaction. As a result of their crystalline structure, gemstones are insoluble.